Now, so the recording started. It's 11:04. We have a very extensive class today, right? That's what I said. Today I'm in next class. Okay. The agenda for today's class. I should say something about the exam as well. How's the exam? I saw two of you submitted it here. Everybody else submitted online. My plan is to finish the grading today. Okay. The exam happened on last week Thursday. Hopefully, I'm not too late yet for the grading. Anything else like the homework? Everybody's done all the homework, right? The past homeworks and everything. Yes. Yeah, the eight. Yeah, so eight. There's another one. Nine. I put it probably right. That one I said I don't. You don't have to do it because I. It's like everything at the last moment. But I did upload the solution manual. So the reason I'm saying that, please do it not for submission, do it by yourself. The solution manual is there. The reason is that homework is related with the exam, the final exam. And I said the final exam is take home, right? Okay. So if you're going to do the practice of those problems, which is something related with these things that I'm covering, that is internal flow, by the way. Okay. The internal flow. The external flow we've done, right? The internal flow means like, fluid flowing through something close conduit, means a pipe, means a duct, like rectangular duct, those sort of thing, right? A copper pipe, right? Anything with that sort. Now, I know in fluid, you guys learn internal flow, right? Everybody remember? What is the critical Reynolds number for internal flow? Yeah, you're right. Absolutely. It's actually 2300 or 3000. Two books. I mean, I don't know about the fluid books. I don't recall which book which used. But heat transfer books, like two common one, the popular one, Incrope and the Essential, they use one use 3000, another one is 2300. Okay. Now, why is that? I did explain that, right? Because there is a big range, right? Because those are not analytical data; those are based on experiments, right? They did bunch of experiment, then they do empirical analysis. Empirical analysis, like people come up with the equation from the experiment, right? So they do the best fit kind of a thing, best fit data or something like that, right? So they come up with this value. Okay, everyone understand? So this 2300 or 3000. So the difference is a big difference, right? The external flow is 500,000 to a million. What is like 500,000 and what is like 2300. It's a big difference. Remember that. So why it's so important? Just like external flow, there is like a laminar and turbulent flow, right? Sorry, just like external heat transfer analysis, we had the laminar and turbulent. The same thing is here as well, right? In internal flow. So this 2300 tells you like when the transition happened from laminar to turbulent. Everybody understand? So the importance here with the heat transfer in terms of heat transfer, Nusselt number and everything changes, means the equation changes. Just like in external flow, you have seen the equation changes, right? When you are laminar, when you are mixed layer, when you are turbulent, all have different equations, right? The same thing is here as well. The other thing, just like in external flow, you guys remember constant heat flux, constant surface temperature has different equations. Everyone remember that? The same thing is here too as well. Okay. The only difference is, if you remember from fluid class, that's kind of related with the fluid. So in internal flow, so see like the laminar, so there is this other thing as well. Let me explain. So in internal flow, uh, when the fluid comes inside a duct or conduit, closed conduit, let me put it this way, then what happens with the fluid? It does have the velocity that it is coming from outside to inside intact, right? So that is part of it. And because of the boundary or means like the conduit wall, it will gonna try to resist the flow, right? Does it make sense? So there will be a boundary layer inside. So there will be two things in combination. One is that they call Friskin flow. You guys remember from fluid class? Friskin flow. You remember, so Friskin flow. Other one is what? The boundary layer, right? So you have these two things. Now, the difference I was explaining, right, from internal to external. Internal, because of that, there is an entrance zone effect. In external, there is no entrance zone effect. In external, what happens when fluid comes on the top of it? I think you remember from fluid class what I'm saying. You took fluid, right? Oh, who's the instructor for fluid for you guys? So you should learn a lot. Okay, you guys remember? So see, what happened in external flow? In external flow, when the flow or fluid hits the external surface, immediately you have laminar layer started, right? You remember that? In internal flow, you see, in external, that fish stream is on the top of it. We don't care about it. We just care about the boundary layer effect, the surface friction, right? In internal flow, what happens? When the fluid comes inside, right, it does have this entrance effect where you are not quite bothered about the laminar or turbulent flow. What you are bothering about? The entrance zone effect. Or there is this thing called fully developed flow. You guys remember that thing? Fully developed flow? No. Yeah, remember, yeah. So fully developed flow is like that. You see, when fluid enters, say like it's a big conduit. I'm the air, right? Fluid. I'm entering inside. So when I'm entering inside, I'm running. I'm fluid, right? I'm running. So I have my fixed velocity, right? But because of say like it's probably like my hands are so big, it's touching on that surface everywhere. My feet are touching, so I'm gonna get a distance, right? That's why there's this boundary layer effect happen. Does it make sense? So this boundary layer, what will happen? It is gonna keep growing inside the pipe, inside this conduit. So I'm going fast, and this boundary layer is gonna keep increasing. So what will happen? Everybody understand? So the boundary layer is gonna increase from all the sides, from top, from bottom, from this side, from this side. At some point, what will happen? It's just the boundary layer. There is no more effect than my speed of running from outside. So I now dictate based on what? Based on the boundary layer effect. Does it make sense? So to portray it here, let me draw something. Then you will understand it better. So see, so this is the pipe, and this is the external flow, right? And I was just talking about this. This is the boundary layer, right? And up to this is the entrance zone effect. So entrance zone, right? And when it comes here, right, the boundary layer, everybody remember from fluid class? Does it ring a bell? So this is called fully developed flow. Let me write it here, fully developed. Now I'm trying to do the comparison, fully developed flow. I'm trying to do the comparison from external to internal. This is internal, right? I'm going to show you the equation shortly. Internal flow. So you see, on fully developed flow, once it develops, it will not going to change. It will going to keep intact to this size, shape of the boundary layer effect. Now, here's the thing. Do you guys remember the Reynolds number equation relationship? I should say equation relationship, which is what? Rho v L divided by mu, right? That's the external flow you use, or L or X. Sometimes you use X, sometimes you use X, right? Remember? But in internal flow, you want to use the length of the pipe or the diameter of the pipe? Diameter of the pipe. So you see, the diameter doesn't change as long as it's the same length of pipe, same diameter of the pipe you're using. So if the diameter is not changing, the Reynolds number is not changing. But in external flow, based on the distance, the Reynolds number keeps changing, right? Internal flow, it doesn't. So that's why what you'll be doing, you first find the Reynolds number for internal flow, and if you find it crosses 2300, that means it is turbulent all over the places. Does it make sense? Unlike the external flow where you have the mixture of laminar and turbulent, you don't have that. You just have turbulent now. If it's more than 2300 or 3000 to be safe side, right? If it's less than that, it's laminar only inside. Okay? So there's a clear distinction from external and internal flow. And the other distinction I established before is this entrance zone effect. You see that? The conical shape Kona stream that I draw, there's the entrance zone effect. In the Kona stream section, what is happening actually? Let me draw the free stream velocity. You see, this velocity, this long line is same here. But here in this zone, what is happening? You have this velocity boundary layer like this, right? Everyone understand? So why it is almost zero close to the surface of the conduit or pipe, whatever you want to say. Why? Because at the surface, it is going to create the maximum amount of resistance to the flow, so it can't move. That's because of the boundary layer growing happen from the surface, right? In fluid class, you guys remember that, right? I don't know if Haskin used it explanation. This could be a perfect example to understand this boundary layer effect, right? You guys remember the boundary layer effect, why it happens? This is one of the classical topics for all engineers. You should know this, okay? It's a bunch of what this thing called, a sheet of wood here, right? So what happened? Say like this is consider these are every layer is like fluid, right? So what happened to that bottom one? Bottom one, when it is touching my hand, it will gonna try to move and it will gonna my hand will gonna resist it to its maximum, right? The top layers, they have less of resistance, right? But because of the bottom resistance, it will gonna propagate to the top layer. And as if like those layers are fluid or air that is flowing. You understand? So that's what the boundary layer. Anyway, any questions so far? That's pretty much it. There is no more fundamental theory I was going to cover. Now, this is the boundary layer fluid thing that I covered. The heat transfer boundary layer would be acted like same. You have learned it in external heat. You remember external flow? So there is a relationship that gets established by a number. Which number dictates the boundary layer of thermal and hydrodynamic? Which Prandtl number. Prandtl number dictates the relationship. Remember the boundary layer thickness. You've done it in one of the homework, right? There is a ratio, so that dictates the Prandtl. Same thing here. It's nothing new. The Prandtl number dictates that, right? Okay, everyone understand? So far, now so the order is like this last 10 minutes I was trying to give you the intro about the internal flow. Now the order before the remainder of the class, I'm going to quickly show you. Quickly means not too like fast, but as fast as I can, the equations relevant for the internal flow, right? Now, the equation, let me give you a heads up. The equation looks a little scary, okay? But it is so easy as well, just like the liquid metal flow, okay? Remember the liquid metal flow equations are so scary, right? But was it that bad? No, you just have to do the computation algebra. It's just algebra. Same thing here too, right? So equations I'm going to show it to you for different cases, right? And then I have two math problems, right? I have only 2 days left, today and next day. The take-home exam, so I won't be doing that much of review, right? So there's not that much to do review. Like these are the problems that you'll be seeing in the final exam, and some of the radiation straightforward question. You can review it from any book and write it by yourself. Okay, online questions I have some. Okay, and oh by the way, finals I keep the points 50%. Okay, so exam 1, 2, and 3. 100, 100, 100, final is 50 because it's like only a small amount of material. Unless if you want me to go through like previous material and then I'm gonna make it 100%. What do you want to do? And if I go with 100, I'm just trying to get the vibe of the class. You want to go with 100 with the previous material comprehensive exam with everything, or you want to just go with small method? 50%. Small or comprehensive? Small stuff. So less stress. Only means that means like up to exam 1, 2, and 3, you kind of achieve most of the points on the exam. Exam is 50% for this class, right? So project is 10%. As long as you submit the project with decent amount of analysis, you will be getting the full course out of it, right? If you submit it, see how easy to get grades in my class. If you submitted all the homework on time, usually on homeworks, I don't point out too much because I know you guys somehow get it solution or whatever. I point out if you have like the engineering format followed, right? If you hastily doing it and trying to do something kind of, then I put up points. If I find like you are really trying hard by yourself, I usually don't take that much of point because I encourage that, like you are trying to do it by yourself, right? That is my model on the homework grade. So basically, I'm trying to say is like homework grade is 30%, right, for this class. So this 30 out of 30, if you submit it on time, then you'll be getting it. But if you are not on time, you'll be getting 5 out of 10, right? You know that. In that case, you'll be getting like 15 points less. Like immediately you will be from A to B, right? Grade wise. I'm just trying to give you the picture, okay? So immediately you are from A to B because the 15 points already gone, right? So then coming to the exam. Exams I'm trying to give you like 2 options, like take home and the in class for both times. So you can kind of catch up the grading. So far I see everybody has good grades, so almost everybody, except a few cases. And then finally is the project. So on the project, you see, all I want you to do the experiment, which I believe everybody did it, right? Everybody did the experiment? Okay. So an analysis part, let me be very clear what I want. Okay, I want you to submit the plot where there should be 5 sets of data, right? 5 sets of data that should have slope. Now you see, if you remember, the project does have the plot, sample plot over there. I put like log plot. So you gotta do log plot. Basically, that means when you're gonna get the Excel data, right? Make sure you convert it to log data. So when you're gonna plot it, you're gonna have a straight line. Make sense? Okay. So make sure you follow that and then get the slopes, okay, and get the edge value doing some calculations, okay. And as long as you have done all the procedure that I said, you'll be getting if the result is correct, 100 out of 100. If the results are not correct, the procedure is 100% correct. You'll be getting 9 out of 10. I'm just trying to give you the idea. If the strategy is wrong, you have major mistakes, then the lowest you're going to get 8 out of 10. Okay, you know what I'm saying? As long as you do everything. If you don't do it, then you're going to lose points. That's obvious. Any question? Final is okay, right? The 50 points, that thing I just said? Yes.
I believe you already answered this, but is the final fully online or do we have an exam date?
No, final is fully online.
Fully take home.
It's a take home. I'm gonna try to remind you again. I already made it and put it in Brightspace. It will be available to you on, I believe, on Thursday. Okay, Thursday. It will be available to you, and it will be due on, when is your final exam date for this class? I did check it and I put the date based on that.
I have that written down.
Is it Thursday? If it's Thursday, then Tuesday? Next week? Tuesday next week? If it's Tuesday, whatever. I mean, I did check it when I put the deadline based on that. So bottom line I'm trying to say is like, whenever is your final exam, the exam due date is on that day. Okay? And it will be available to you on Thursday.
The exam date, if it wasn't a take home, would have been Tuesday 10 to 11:50.
That means the exam is due on Tuesday, end of Tuesday. That's how I put it. Alright? Any question? Alright, now enough talking happened. Everyone understand? Everybody have a good grasp on this internal flow? If I'm gonna quiz you, you can do it? I don't have time for quiz, but if I can quiz it, you can do it, right? That's the confidence I want from everyone. Alright, so now let me go through the equations, okay? Oh, by the way, I didn't quite show you this thing. I haven't done any math, and I don't have plan to do any math either. But in your book, you'd be seeing, you see, the unheated starting length. What does it mean? This is not external, internal flow, by the way. So unheated. Isaac, just take a look here. I'm showing something. You see, unheated starting length means, say like this is the plate, right? Say like you have some coil only sitting here, right? So, and this coil is producing constant heat flux, or if you have a different temperature here compared to here, right? So what will happen when the fluid flow is come on the top of it, right? If you understand what I'm saying, when the fluid flow is coming on the top of it, what will happen? Because of this zone has a constant heat flux or constant surface temperature, the heat transfer starts from here, not here, and that is what you are seeing here, right? Two lines. The top line is the hydrodynamic boundary layer. The bottom one is for not the bottom one, the right one. I should say bottom one, or bottom one, you can say bottom one. The bottom one is for the thermal boundary layer, right? So, and everything else follows the same pattern, right? You see the Nusselt number equation, which is the Reynolds number. It looks scary. And again, all the equations here in convection, even they look scary, these are not scary stuff. These are just algebra, okay? You just have to plug the values, find the values, plug the values, and find the H value and find the Q value. That's the goal, ultimately. Any question on that? You understand? The difficult thing is conduction. And even more difficult thing is radiation. I took an advanced radiation class during my PhD period, right? And my boss is a scientist, big scientist on radiation, right? He's a big guy on radiation. He wrote a book also. So radiation could be very, very, very difficult thing, okay? Anyway, moving on. Okay, another take-home message you need to know. You know when radiation is important? Anybody know? I mean, you have done some radiation equation, right? There's a basic equation. Remember that, right? Remember sigma, delta, epsilon, A, T to the power 4 minus T to the power 4, right? Remember that? That equation you use, right? But you guys remember when radiation is important? No?
I
don't.
Huh? Application? That is partially true. I will explain. Anybody else have any comment? The first thing, that's the first thing. Anytime you have a high difference in temperature, radiation becomes significant. Example could be, pretty much every day you use the oven. The oven does have either forced convection oven or natural convection oven. If it's a natural convection oven, the radiation actually dictates that, even though by convection the cooking happens, right? Okay. Now remember the other thing I said, right? When the heat transfer happens, these are physical phenomena. We people come up with the equations, classify radiation, convection, and the physical phenomena doesn't have any clue it is radiation. That why I'm saying that? Because anytime the heat transfer happens, every mode of heat transfer happens. Does it make sense? The conduction happens, convection happens, radiation happens. Now, depending on the situation, which one is significant, that's what your goal is. Now, come back to Chelsea's comment, like application. It is so important. Radiation is based on application as well. Like, whenever you deal with combustion, you know what is combustion, right? Like, something is burning. Radiation is the main power play on that, right? Okay, whenever you're dealing with interstitial these things, right? There's no air, nothing, no touching. Radiation is the main in space. Yeah, very important thing in space. If you ever had the opportunity to work for NASA or like nowadays Elon Musk X, right? Yeah. So anyway, so radiation is important, right? Anyway, now at least you know why radiation is important, right? After this class, after graduating from here, if somebody asks you, why do you care about radiation? Yes, radiation is important. Whenever the temperature is important. Anyway, I didn't even touch the main thing yet. The main thing is from here. Okay. All right. The equations. Everybody focus, please. Focus, everyone. This is what you are. This is what you wanna put all your focus, because these are the equation you'll be using. Okay. First of all, let's start with that. So first thing first, these are the equations from Incropera book. And by the way, Incropera is the most common book out there. Okay. Most popular book in the world for heat transfer. All right. So TM is something that you're seeing it for first time. TM is called mean temperature. So you guys remember film temperature, right? From external flow. What is the film temperature? Average of surface and the air temperature, right? Now I remember when I was undergrad, like you guys, and my instructor used to take out points if I couldn't explore the properties, the thermophysical properties like the rho, Cp, and other things, right? Based on film temperature. If I could have just used the TS, surface temperature, or the fluid temperature to explore those properties, I usually always get a reduction on the points, okay? And back home it was serious matter. So I mean, just trying to encourage you, make sure why you are using the film temperature. The same thing kind of here too. Okay. So the mean temperature. Okay. Now there is a difference between the film temperature and mean temperature. Obviously, the mean temperature is referring to. You see, you gotta understand first the temperature profile, right? What happened inside the pipe or conduit? Inside the pipe or conduit, which you are following what I'm saying. So inside the pipe or conduit, you have the temperatures obviously varies along the free stream, right? Or the fluid flow. So you need to explore the properties and mean temperature of this different section of the fluid inside the pipe. Does it make sense? So that's the mean temperature. Now, how do you find it? I mean, usually you find it by doing integration. And if you're going to start reading through the internal flow chapter, which is chapter 8, by the way, if I'm not mistaken, right? So if you're going to start reading through chapter 8 from your textbook, you'll be seeing they have like pages after pages explaining how to do the integration, right? And how to find the mean temperature and the explanation of that. And I highly encourage all of you to read that. Because of the scope of the class, 2 class for three things, three credit hours, it is not possible for me to cover that. And then back home we had 2 classes. And the mean temperature, I remember my instructor spent one week on the mean temperature. So he has the luxury. I didn't. Okay. So I mean I don't have time. Okay. So but I'm encouraging you to read through that. Interesting stuff. And I was just trying to give you the gist. What is the mean temperature? Do you understand? You are basically integrating the fluid layer temperature inside. So you can explore the properties and average temperature for the whole fluid. Does it make sense? That's the mean temperature. So these are the things that is so important. The entrance zone, I'd like to highlight that. Entrance zone and fully developed zone. This thing I explained already, right? So in the pipe, you have this XFDH. I'm going to write this thing XFDH. Okay, you really have to understand what does it means. Let's look at the subscript. Okay, the subscript has FD means, any idea from the
Fully
fully developed, fully developed. So the transition happened. You see, in external flow, we had the axis. Anybody remember what is axis? Laminar to turbidal transition, right? Remember critical Reynolds number R is REC R XC. Based on that, we remember that, right? In internal flow, we don't have to deal with this thing anymore, right? The critical point where the laminar to turbulent happened, because in internal flow, that's a common sense question. If I'm going to ask you, right, in exam, so in internal flow, it's either laminar or turbulent, because the diameter of the conduit or pipe or whatever is the same, right? This makes sense? So the Reynolds number will be same. If the Reynolds number will be same, as long as it's more than or less than 2300, you already know the whole pipe has laminar or turbulent, right? So the thing that you see on external flow comparable to here is the transition where the entrance zone diminished to fully developed. So FD is fully developed and H means hydrodynamic. You understand that? So you would be seeing time to time X, FD, T as well. T means thermal, right? And they can use different subscript as well. So bottom line, I'm trying to give you the understanding here. So this delta is the boundary layer, and this is use the free stream. You see the different shade here inside, and this boundary layer is a little bit darker shade, right? You see that in the sketch. If you're seeing that boundary layer a little bit darker shade, right? And then you have the fully developed. Once the fully developed happen, you have no more lighter shade anymore, right? Right? Okay. So fully developed XFDH, where the transition happened, the transition is not from laminar to turbulent. The transition is from entrance to fully developed. You understand that? Again, for internal flow, this XFD, as you can see, the internal flow, this XFDH is where the transition happened from entrance zone to fully developed. For external flow, this XC, where the transition happened from laminar to turbulent. Remember that? Everybody? Alright. Now you will gonna start it to understand it more. Anybody else? Anybody say? Alright. Okay, so far everybody's with me? Okay. I wanted to do it first, but this is the first time you're learning that. If I'm gonna go fast, you're gonna be learning some bunch of equations. You're gonna be learning possibly doing some math, and pretty soon after the semester ends, you're gonna forget everything, and you're not gonna learn what is internal flow. Okay, these are the main things. The math you may forget, but this thing that I'm explaining, if you listen properly, you're gonna remember it. Okay, as long as if you read it at home. These are important stuff. All right, so now let's move on to a little bit more stuff. So combined entry zone or entry length. Okay, so there is this new number that they use. What is this number? Gratz number. What is the Gratz number? It is the combination of Reynolds Prandtl and the dimension, diameter and the length of the pipe, right? Okay, what does the Gratz number do? The Gratz number, you don't have to remember the Gratz number by equation itself, like Reynolds Prandtl or Nusselt. But if you are given with this kind of situation where you are exploring the entry length heat transfer, okay, you can explore the Gratz number by using this equation and plug this value of the Gratz number here, and do this complex looking math algebra to find the Nusselt number. Once you have the Nusselt number, what you can do with that? You can find the Q value for the pipe. Q is the heat transfer that happened. Now take a look at I did give you the warning before, right? The right side of equation could be looking very scary. Take a look, it's just simply algebra. If you have an advanced calculator, you just simply start to plug all the values, you'll be getting the results. Now, there's one thing here, this 10H. You guys are familiar with the 10H? No? 10 hyperbolic. So you need calculator, there's an option to find the value of the 10H. Okay? There should be. In geometry class, some kind of advanced calculus you should be able to learn. Don't worry, this is like some form of math. Your calculator does have that option. Any programming does have that option. Okay. Other than that, what you are trying to do here, you are trying to find the Nusselt number. Oh, by the way, let's focus on the Nusselt number on this case, right? So Nusselt number. So Nusselt number and you guys remember for external flow, what is the subscript that you guys use? For external flow, you usually use like L or X, right? Everybody remember that? You usually use that subscript. What is the subscript that you are using for internal flow? D, diameter. So if you have a line on the top of Nusselt number, what does it mean? Is it a local Nusselt number or average Nusselt number? It's the average. Now you know that for sure. And this Nusselt number, is it like HL by K? You guys remember that equation for external flow? Or sometimes you use, I know, sometimes you use X, right? But what you would be using here? D, thank you. So the D is the diameter, right? Let me write it. So this is the diameter. Everyone's taking class note? Understand? These are important stuff I'm covering, very important. So what we are doing here, by the way, so we had this Nusselt number, okay, and I forgot to put a line on the top. This H is average heat transfer coefficient, right? And from this complex looking equation, where the tan H, something new that most of you understand, most of you learned today, right? Tan hyperbolic. This complex looking equation, no matter how complex it looks, you should be able to figure out most of the property, right, on the complex equation. Now, let's go one by one. Grass number had this Reynolds number. Okay, so this Reynolds number here, the Reynolds number here, usually we used to write this rho VD divided by, usually we used to write, rho VL or X divided by mu. What you should be writing instead of L, Isaac, here in this internal flow? Diameter, right? Because this the internal flow, the length is not that important here, right? So the diameter you will be putting, and that's the reason you put a subscript D. Did you see that? So that's the Reynolds number. Everybody got it? Okay, so this Prandtl number here, this Prandtl number, why you are getting the Prandtl number value, by the way? From the table appendix. You've done it before. Okay, so now usually I remember Mitch was asking, okay, what temperature we'll be using, where we're going to find the year, right? Remember that in the exam? So I was just saying like, okay, go to that table, and he was there and he found like a bunch of temperatures. He was wondering which one to use, right? Then you probably use it for film temperature, right? If I'm not mistaken. Now, what temperature you would be using in that case? The mean temperature. You don't have a film temperature that you want to use here, right, Matt? So the mean temperature you'll be using. Now, you don't know how to find the mean temperature, right? Remember, I was saying like that's a complex, integration or whatever. Believe me, I didn't do integration. Probably I did it 1 or 2 times in my life for finding mean temperature, right? But most of the time, you can find the mean temperature, or the mean temperature is given, or there are straightforward equations for that. So don't worry too much on that. Okay, just want to explain what is the mean temperature, what are the properties you'll be finding. What properties you'll be finding, therefore, and mean temperature, Prandtl number. What else? Mu, right? The viscosity. What else? The rho, depending on which mu you are getting. Either you are getting nu, no rho. Nu is the kinematic viscosity. Everybody remember that? Or if you are getting mu, then you need the rho. Rho is the density. Okay, how you guys are doing? That was good. Any questions so far? Does it feel like too much going on? No? Okay.
Even if it did, we could watch it later.
I'm sorry. It comes to this situation, like, I had to go for the conference 2 days. I could have get one more day, then it could be even more smoother. But there is a problem. I can upload some more video lecture if you are interested. I have some. My lecture, my own lecture. Okay. So internal flow. So in internal flow here, you have this equation, Nusselt number equation for turbulent. Okay. Nusselt number equation for turbulent again. Now that's where I usually lose some of the students. Okay. So there is this laminar equation somewhere as well. Yeah, this is the internal flow. Let me highlight that. That's the laminar equation. Now, that's where I sometimes lose a student as well. Okay. You see, you have this two situation. Q double prime. What is Q double prime? Heat flux, right? So we have constant heat flux situation, which you are seeing it. The equation I'm highlighting. You have T as a constant means constant surface temperature, right? So you see, you have this two Nusselt number equation. So what are the values you are seeing here, Matt? Some constant numbers, right? So I got sometimes students get confused. Why this is so simple? Okay, because compared to what you have seen, like the complex equation here, these are simple, very simple. If the flow is laminar, okay, you can even deduce that analytically. That value that you are seeing here. Remember, all the equations that you are seeing here are those analytical equations, the convection equation, or experimental equation. You guys know that, right? I did probably mention all the equations that you are seeing here in convection, the experimental equation, okay? Except in very few cases, like in this case, you can analytically determine this. Does it make sense? Okay. So Mitch, you have the experimental data. How are you gonna come up with the equation? The easiest way, the book. No, you have to say like I'm saying all the equations that we use for Nusselt number so far are experimental equation. Now, what is experimental equation? Then some scientists probably have some grad students. They are taking so many data, right? Once they have the data, they come up with some equation. How they come up with the equation? Anybody have any idea from the data? Analyze the graph. That's a very good answer. That's exactly what you're doing on the project, right? What you're doing on the project, even the simplest thing, right? You are getting the data, right? Everybody's getting the data. What are you going to do with the data? You are plotting and you are getting the equation for a straight line and you're getting the slope value, right? Does it make sense? So you're coming up the equation, the same thing. They call this thing, if the equations comes from experiment, they call this thing, there is a term for that. Anybody heard about it? Empirical equation? Did you heard about it? Empirical equation. This is important stuff. You want to know this, okay? Well, if anyone is saying what is empirical equation, that means that question came from not analysis, right? It came from the experiment, okay? You understand? So the reason I emphasize on this value of Nusselt number here, these two value of Nusselt number for laminar flow. Let me write it again, the same thing. That way you may highlight it. Everybody take the class note for laminar flow, internal flow, right? Laminar internal flow. You have this Nusselt number 4.36. That's for constant heat flux, right? And you have this Nusselt number. Don't forget to put a line on the top. 3.66, which is the surface temperature constant. You understand? So that's simple. These are the two conditions. Okay, don't get confused with this. Okay, these are just a condition. All right. Now the entrance length or entrance zone. You guys already remember what is entrance, right? This is the entrance zone, right? What if you are interested to find the heat transfer on the entrance zone? This point, everyone understand what I'm trying to show here? The entrance zone. See, you have the fully developed flow starting from here, right? Everybody remember the entrance zone effect? Right? So in entrance zone, there are two sections, right, David? The left section is the entrance zone itself. The right section is the what? The fully developed zone, right? So if you are interested to find the heat transfer that happened in the entrance zone, how are you going to find it? Believe me, when I was doing my research in PhD, I had to deal with the entrance zone heavily. It's entrance is heavily because I had a situation where I was trying to be mimicking the cloud droplet growth in experimental setup. Cloud means the cloud droplet growth in the experimental setup. Okay, so I had a big pipe that I created, right? Aluminum pipe. I galvanized that thing, and then I had this steam was coming on the pipe, right? And that steam was slowly getting droplet, right? At some point by doing some mechanism, I'm not explaining that, but there was this entrance zone. So I had to take care of such a way the setup and the flow and everything. So the entrance zone effect is minimal. Does it make sense? If you are getting it, what I'm saying? The entrance zone is so important because the entrance zone has a different heat transfer rate, right? Right? So entrance zone has a different heat transfer rate. Fully developed zone is a different heat transfer rate. You're seeing me pausing on something intentionally, just to give you more time to absorb this. When I'm gonna go to the math, so when I'm gonna go to the math, it's not unintentionally. I'm intentionally doing it. Okay, I'm intentionally giving you more time to absorb it. Okay, when I'm gonna go into the math, so you can connect. Otherwise, if I'm gonna jump too fast, when I'm going to the math, you're gonna feel like lost. So now everybody understand entry zone. So everybody understand there is a difference of heat transfer in entry zone, right, Mitch? Compared to the fully developed. Fully developed, you are expecting different equation, right? Yeah, definitely, right? So this is the entry zone equation. You see, as it does the entry zone equation looks like scary. It is kind of sort of right compared to the laminar flow itself, but the entry zone equation has like this Reynolds DL and some constant numbers. That's it. Okay. It does look scary, but it is not as scary. Nusselt number left side on the entry zone is again the same. If you remember the Nusselt number relationship, it is HD over K, right? So HD over K. Everyone got it so far? I'm almost done actually with the equations. Okay. So now so far what did we cover? We did cover first it started with Krebs number. Remember we had a Nusselt number equation over here. Okay. That's when you have an entrance zone. Let me go back on that. That's when you have an entrance zone. So this is what I was saying, right? When you have an entrance zone, you see combined entry length. When you have a combined entry length, okay, that is the equation I first covered. Remember, there's this chain and everything. Now that equation is a combination of entrance zone and fully developed. Does it make sense? As like you guys remember the combined flow, like laminar and turbulent in external flow. Remember the mixed layer. This is compared to this thing as mixed layer. That means it has the entrance zone. That you understand, right? The entrance zone and fully developed. That equation is for that. The equation previously I showed. Three more equations I showed. Two of them has some constant number. One for the constant in flux. Another one is for the constant surface temperature. Those are for laminar or turbulent. The laminar. Those are for laminar. So I did show you those two equations. And then I was showing what if you are not interested for mixed layer. You are only interested for entrance zone. Remember, I was showing it to you that equation 3.66 plus blah blah. That equation, Reynolds combination. That one is for entrance zone. So what is left now? What more equation you need? You have the laminar equations. You have the entrance zone equation. You have the combined equations. What equations are missing? What more equation you'd like to explore? Turbulent, right? You will get it? The turbulent equations are missing yet, right? Turbulent, which one? Turbulent fully developed. Those are missing, right? Instead, so turbulent fully developed equations are here. These are the turbulent fully developed equation. Everybody see that? So you may want to write this equation with me. So Nusselt number 0.023, Reynolds number D, and I'm gonna very soon I'm gonna bring you to the fluid class. Okay, just hold the thought just for a while. Okay, you'll be seeing. You guys remember the Moody chart? How many of you remember the Moody chart? That based on mood. Just one? Moody chart? How many of you?
I remember talking about it. I don't remember.
I have more of an excuse. I took it almost 10 years ago.
Oh, wait. Moody chart. Remember the mood? Based on mood? Vaguely. Therefore, remember the Moody chart? No? Isaac, no? Kind of ringing bell. That's why this course has a prerequisite of fluid
I
mechanics.
remember going over it. I couldn't tell you anything about it.
It's all right. So you see, the Moody chart itself is going to take in fluid class. You're supposed to come into fluid class. It's supposed to in fluid class. It should take like several classes for you to understand, like 2, 3 full class. Just the Moody chart itself. Now here we're assuming you know Moody chart and you know how to use the Moody chart to find some values. You use this equation. What equation I'm talking? Take a look here. When you're dealing with the turbulent flow, you need the value of this friction factor. Those who remember the Moody chart, you remember the friction factor F? That friction factor, you're going to find it from the Moody chart. And as you take a look on the other terms of the equation, I don't know if I discourage any of you. See, everything else is like the Reynolds, Prandtl, and some number, right? That is straightforward case. But the F value, as long as you find it from Moody chart, you're good. Does it make sense? Then you can find the Nusselt number for what? For the turbulent flow, internal flow. Okay. So these equation you will be using. Okay, this equation you will be using when you are dealing with the Reynolds number in between 3,000 to this 5 million. Okay, so this is another equation, but there is an easier equation as well. Okay, and oftentimes when you will be learning heat transfer, always remember that. Okay, so in heat transfer for one certain application, there are multiple equations. Okay, even for this turbulent flow, there are multiple equations. Why? Because say like you are a professor, you have a big research group, you come up with the equation, and I do have a big research group, I come up with another equation. I was claiming this is more correct equation, you are claiming both publish the results, and they both may come up in the textbook. Okay, because all are experimental equations. Does it make sense? Everyone understand? Okay, so that's why, look, and you're seeing two equations over there, right? So both has kind of the same conditions. You guys remember these are the conditions, right? On the right side there I put here that as long as the Prandtl number value in between that. Now you guys have a very good idea about the Prandtl number, right? Because you in homework number 6, in problem number 1, you have seen for water, air, engine oil, right? The thermal boundary layer and the velocity boundary layer. You guys remember the Prandtl number value for different materials to be completely different, right? That's what dictates which equation to use. Now this Reynolds number here, the critical Reynolds number, depending on, remember I was saying like, in Cropper is 2300, Sanjel is 3000, right? Some other public, maybe I'm going to write a book next year and I'm going to say, no, it's not 3000. Yeah, based on this journal, 3200 I like, right? And it's not like I'm claiming out of nowhere. I'm going to refer. So yeah, this thing happens. So basically, all I'm trying to say here, you have these two equations for the same application. If the second one feels scary, if I don't specify, use the second one, use the first one. But you really need to know the Moody chart, the friction factor F, in order to understand the internal flow for sure. Okay, so that's why I'm going to explain the Moody chart and the F. How do I find the value of the F? How do I find the value of the F? From the chart. Let me explain the chart, and that's the last thing that I'll be covering. Actually, I don't have the chart, but I remember the chart very well. I can draw it. But in your book, you have the chart, okay? The chart should look like something like this. So you have the friction factor here. You have the Reynolds number here. I remember it by heart. That many times I read it or learn it, okay? So you have this E by D. These are called, the D is the diameter. E is the smoothness of the pipe. Different pipe have different smoothness, right? Based on that, they have these lines like this, right? Does it make sense? Different E by D. So if you know the E by D value, if you know the Reynolds number value, you're going to come up with the value of the friction factor from the Moody chart. So this is the Moody chart. Everyone understand so far? That's all the Moody chart. Now in the Moody chart, oftentimes you'll be seeing a line. That line is for laminar flow. And this is for turbulent. Again, what Moody chart do? Moody chart gives you the value for the turbulent. I know I give you so much. Okay, I gotta now stop and do at least one math. I have more than 20 minutes left. I have a very easy math today that I would like to do. In next class, I have a very complex math. So that could be the good idea, right? In next class, I have a very complex math for internal flow. So I'm going to explain that complex one that requires a little bit more equation. A little bit, not too much, okay? Those equations are here. I don't want to explain that, those two equations. If I'm going to start to explain those equations, I'm going to lose most of you, okay? You see this page equation? I highly encourage. So far, whatever I explained, I don't know. Do you guys feel like you absorb all of it? All of it? If not, I highly encourage you to read through the book after you're done with the class. This page of equation, as I said, if I'm going to start explaining those, I'm going to eat up all the class time. Because I just don't want to explain something when I feel like my students don't understand something. Okay? So basically, the idea could be today, out of these 20 minutes, I can comfortably do the problem. Like out of two problems, one problem I can do for sure. That is the easier one. Okay, I'm gonna do that problem. Okay, and then next class I'm gonna go through this page only. This page means this page only, and that complex math that I'm gonna do. And radiation, I already did at the beginning of the semester. I'll possibly talk a little bit about the radiation. As I said, in the final, you'll be seeing some terms. Those terms I'm gonna explain. I'm gonna try to talk about those terms. Okay, whatever you'll be seeing in the final. Okay, so you won't be getting something out of nowhere. Okay, yeah, that's the plan. Any question? Is it ready for the math? Everyone, get pen and paper. Get pen and paper ready. Okay. Okay, I don't want to do the summary again because we don't have time with all the equations and everything that I covered so far. So I'm gonna go back to the class lecture, and this is the problem that I'm gonna cover. Okay, so here let me start reading the problem. Okay, everybody's with me? So this is the problem actually here. So you have the hot air with a mass flow rate is given. That's another very important thing here. Okay, the mass flow rate m dot is given. So this hot air is flowing with the m dot value is given as 0.01 kg per second through an uninsulated sheet metal duct with the diameter value is given. So this is the duct they are referring, and the diameter is 0.35. And the crawl space, it's in the crawl space. Hot air enter at 103 degrees Celsius. So that's the entrance temperature. They write it as like TMO, right? 103 degrees Celsius. And after a distance L equal to 5 meter, so this L equal to 5 meter, the length of the pipe, right? It cools down to 85 degrees. So they write it this way: TML equal 85 degree. Okay, those are the symbols they use, right? So entrance and exit temperature given, they have the duct diameter given, they have the length of the duct is given. Okay, and then they're asking find the Reynolds number inside the duct and thermal and velocity entrance length of the flow. Okay, so thermal and velocity entrance, but the velocity entrance length, you guys remember FDH? Everybody remember that term I was explaining? FD means what, Isaac? Fully developed. Remember that H means hydraulic, right? So hydraulic means velocity, right? Is the same, and thermal is the T. Anyway, so these are the things given. The other things given, obviously, here the infinity T infinity is the ambient temperature. Okay, ambient. You guys are familiar with the term ambient temperature? How many of you are familiar with the term ambient temperature? You? Anybody else? So ambient. Let me write that. That's the key word, right? Ambient. AMBIENT. Ambient temperature. If after you graduate in mechanical and don't know what is ambient temperature, it's not too good. Okay, the ambient temperature means the ambient temperature. Ambient means the air around you, right? So they said the ambient temperature is 0 degrees Celsius, right? You're not probably seeing it like now, you're seeing it better, right? So they use the symbol T infinity is 0 degrees Celsius, and they gave you the value of H0 for ambient temperature 6 watt per meter square Kelvin. I know it's not shown very clearly over there because of this issue with this bad projector. Okay, but it's showing clear here in my side. Okay, anyway, I upload this material. I haven't yet, so I'm gonna upload this material as well. Okay, in Brightspace. Any questions so far? Okay, to give you a wrap up, what the question is giving you, they gave you first of all a pipe or conduit, a duct, whatever you say, like a round duct. Okay, the diameter given, the length of the pipe or duct is given as like 5 meter, the diameter is given as 0.35 or whatever, right? 0.35 meter, right? And then they were saying like the entrance temperature TM0 is given, and the exit temperature of the air, right? Whatever is going to the pipe is given as TML, right? Now here you see it runs in the cold space, possibly in winter, right? That's why the entrance temperature is much higher. 103 degrees Celsius, exit temperature is 85. In crawl space, usually anybody seen crawl space? It's not common in up in north side. It's very common in south, right? Anybody is familiar with the crawl space?
They're pretty common up here too.
It's common here as well.
I do HVAC work and I've seen pretty often.
Oh yeah, I thought everybody put like here the basement, right? So the crawl space is like as if like you don't have a basement and it's running underneath, right? And obviously crawl space is exposed to ambient, and 0 degree is common in winter, right? You can design the temperature that way. So 0 degrees usually not that much of flow happen. You can expect this is the natural convection. And usually the forced convection, that's why you're doing the experiment. You'll be seeing it, right? When you'll be getting the H value should be more than 10, 20 or something. The free convection values are usually very less, right? The 6 watt per meter square Kelvin given, that is kind of saying like it's a free convection something happening. In crawl space, usually you don't expect that much of wind because usually they have that blockage or something around the house, okay? So you can expect like mimicking the natural convection happening. That's why the H value is like 6 something, okay? It's not 10, 20. If it crosses like the H value more than 50 or 100, that means you are getting very high prostate heat transfer, okay? To give you some number idea as well, right? Make sense? Okay, moving to the question itself. So question asking you, find the boundary layer thickness. And I'll be asking you, find the AQ value as well, if you can do it, okay? How are you going to approach it? Before you start to solve, let's try to think about how you're going to approach it. Means how you're going to solve it. By the way, I do have the steps here. I'll talk about it later. But just to give you overview. First thing for convection, internal, external, doesn't matter. What is the first thing you find? Reynolds number. Reynolds number, right? Why? For external obvious reason, it's laminar turbulent. You need to find it. Based on that, you come up with the equation and find the H value, right? I said, what do you need to find the Reynolds number here also? As it is saying, to find the appropriate equation, right? Whether the laminar or turbulent. So the first thing you would be finding the Reynolds number for sure, right? Everybody got it? So once you have the Reynolds number, so they have been asking you to find the Reynolds number, right? Then they're asking you to find the velocity and thermal boundary layer. Now, those two equations, you have done it for external flow. You haven't done it for internal flow. I'm going to give you those two equations, okay? All right? It was good so far? Okay. So let's start with the givens. So first givens are for sure. So this m dot is given as, even though I have this thing jotted out this way, I'm going to write it anyway by myself. So the givens are the mass flow rate m dot. You see the explanation is here. I'm skipping the text just for saving time. So the mass flow rate value is given as 0.01 kg per second. What else? The diameter, pipe diameter, I did explain it here on the side. So it is given as 0.35 meter. Anybody found the Reynolds number yet? No, it is not that easy. You have to find the properties, right? Okay, so then what? Then the length of the pipe. What is the length of the pipe given? It is 5 meter, right? All right, so the ER entrance temperature, TMI, that's the ER entering temperature. This one, even though I wrote it over there, I'm going to still write it. So I'm going to write it ER entering temperature. And I'm going to write TMP dot. Which you are taking class note? Take the class note. So 103 degrees Celsius, right? And then you have this ER exit temperature, right? Anybody remember what is the ER exit temperature? (85 degrees Celsius). What is the ER temperature or ambient temperature? 0 degree. Ambient temp. Okay, so there's another thing to understand. You guys remember that probably from previous classes as well. Anyway, anytime you see a infinity subscript, that means it's an outside temperature or reactor temperature. Why put infinity? Anybody else have a question? Infinity means as if like you are zooming. Infinite amount of space is the same temperature, right? It's a perfect situation. Obviously, that's not the case always, right? That's why they use that infinity. Okay, so what else? So then the properties, okay? So these properties, I have it here though, but I'm going to write it anyway. So the properties, you're going to explore. What temperature you're going to explore the properties in this case? Is it the surface temperature? It's the surface temperature. Let me put it this way. Is it the surface temperature? Is it the mean temperature? Is it the film temperature? Mean temperature. Okay, already I tried to establish that. So let's assume the bulk mean temperature. So bulk mean temperature Tm is 367 Kelvin. Okay, So this bulk mean temperature, you may be wondering how you're going to find this value of the bulk mean temperature, right? So the way you can find the bulk mean temperature is you gotta do this Tm entrance temperature and Tm exit temperature, right? That's your bulk mean temperature. Now, if you want to do the math, remember I was saying you don't have to do integration. I don't recall how many times I did the integration, probably 1 or 2 times in my life, right? Even though I did it so many times, right? But the bulk mean temperature is, what do you have, like 103 plus 85, right? Divided by 2 plus 273, remember, right? You got to add 273 degrees Celsius to find the Kelvin. Why did I find it in Kelvin? You may argue and say, okay, why I'm going to this in Kelvin? Because in the book, in Cropera book, they have the properties in Kelvin. Which you remember the properties are in Kelvin, right? Air temperature. So you need to get the properties in Kelvin. There's no way around. So this 367, once you have that, let me start to write the property value. And you will be seeing shortly why do you need that. So these are the properties that you're going to need. At least first 3 for sure you're going to need, right? So this first one, is it a kinematic viscosity or dynamic viscosity? Mu. We learned 2 things, mu and nu. Nu is the kinematic and mu is the dynamic viscosity, right? Everybody remember that? I'm not going to write it though. I am trying to save some time and I'm trying to talk more than wasting time. So 2.117 10 to the power minus 5 Newton meter second. So the Prandtl number is 0.698. Do I have a unit for the Prandtl number? Because it's a number, right? Dimensionless thing. Always remember. Prandtl number, Russell number, Nusselt number, Prandtl number, Gress number, Reynolds number. No, nothing has any unit, right? These are the numbers. Dimensionless numbers. So what is the K value here that we are writing? Is it the K value for the pipe or the K value for the air? Yeah, you guys already know that, right? All right, so K is the conductivity. Remember, therefore I was saying at the beginning, right? When the heat transfer happening, right, from the air to the pipe, heat transfer, the air doesn't have any idea, pipe doesn't have an idea what mode of heat transfer it has. It doesn't care, right? It's a physical phenomenon happening, natural thing. We people come up with the equation, try to quantify how much of the heat transfer happened, right? So basically what I'm saying here, even though convection equation that we are trying to explore, still there is a conduction happening, because as long as there is a K value, there is conduction happening, right? But it's so minimum. So we always do that optimization, right? Which one is significant here? Convection is significant here when the fluid is flowing, but the conduction is still there. Just try to understand that, right? Radiation is still there, but we are not counting them because those are too small to consider, right? Yes. Okay, I'll help you. So this value of K, I wrote it like 0.0306.
Okay, thank you.
Yes, thank you. So the CP is the final thing. Anybody remember what is CP? Is specific heat at constant pressure. P subscript is referred for pressure. Okay. All right. So that's it. Now, I'd like to go to the solution. I do have like still 7-8 minutes left, which could be enough to deal with this problem comfortably. The solution. I'd like to deal with the solution. Okay. Remember, I was talking about the Reynolds number. Everybody remember that? What is the equation for that? Rho Vd divided by mu. The question is, do you have all those values that we are seeing here? The rho, I didn't quite write it, but I can find it from the same table. For air, it's not a difficult thing to find. Zoom, we find it, rho. But question is, can you find the velocity value? Did they give you the velocity? They have the mass flow. So Logan mentioned here, you better somehow figure out the velocity from the mass flow, right? And that's where the fluid mechanics come again here, because this class is a prerequisite fluid mechanics. Okay, if you'd like to understand convection, you need to know fluid mechanics. Not like all ins and out, but you need to know the mass flow rate equation. What is the mass flow rate equation? M dot equal to, anybody remember? Rho density, A cross section, V velocity. Everybody remember that now? So M dot equal to rho A V. Now, if you're gonna do some magic here, means some derivation and everything, you're gonna come up with this equation with the mass flow rate itself. I can do the derivation in other time, but not now. We don't have time. in your book, by the way, they have this derivation. Bottom line, you're going to come up with this equation: 4m dot divided by p mu. By the way, this p is called perimeter. Perimeter. Now, what is this perimeter? What is this perimeter for this cylindrical shape conduit or pipe? What is the perimeter of a pipe? If the diameter is d, anyone? Oh, I'm sorry, what is happening here? So if the diameter is d, the perimeter p equal pi d. Everyone remember that? Pi d. You guys remember what is perimeter? Let me highlight. Let me see if I can highlight the red color. So this is the perimeter, right? This is geometry class, right? This is the perimeter, pi d. All right, so let me write it then. So this is the perimeter p equal to pi d. You're going to find the value of the pi d. By the way, pi d can be written as 2 pi r. It's the same thing, right? That should be something very common. Okay, so now you have this. Oh, I gotta put this d subscript here. So 4m dot 2. Let me still stick with the p for now. P mu, and then I'll be writing 4m dot 2 pi. Actually pi d. I don't have the radius directly. I have the diameter directly, mu. Can you find the value of Reynolds number by using this? Should be, right? You guys are not taking class notes? 0.01 kg per second, and then pi 0.35 meter multiplied 2.117 10 to the power minus 5 Newton meter second, right? What is the value of Reynolds number we're going to get? It is 1723.4. Now this value is telling you we're dealing with 1723. I mean, this, I'm extremely sorry. This thing sucks. It just doesn't show you properly. This 1723.4, what does it tell you? It's a turbulent flow as a laminar flow. So you should be writing that, specifying that, go from there. So you should be writing, okay, so we have this thing is less than RDC. Now, what is this? This is the critical Reynolds, let's say, number. And we know critical Reynolds number is either 2300 or sometimes people use 3000, right? This is Incropera. This is Sangel. Two books is two different values. I did talk about it. All right, so we know this is laminar flow. This is laminar flow. So what is laminar flow again? And what is that we have seen here? You see, you have this entrance zone effect. So I would expect you to draw the plot every time you're doing the problem in finals. So this is entrance zone. This entrance zone, let me write it clearly. Entrance. And this is the fully developed zone, right? Now the question is actually asking you to find where the entrance zone ends or where the transition happened to fully developed, not where the laminar and turbulent. This is what we found it because they're asking you to find the Reynolds number, which is fine. You come up with the Reynolds number is laminar, but where the transition happened, what are the equations that you'll be using for that? So let me give you those equations. The first equation is, so velocity, so there are like two equations. First of all, the velocity boundary layer. How many of you remember the BL means boundary layer? Everyone, right? So first one is the velocity boundary layer. I'm going to give you these two equations and I'm going to let you solve it by yourself, okay? Let's see if you can do that. 0.05 Reynolds, okay? So this XFD is what again? This is called, XFD is what? the length where the fully developed hydrodynamic boundary layer happen, right? X FDH. So can you find that value of X FDH, which would be again 0.05 multiplied D multiplied Reynolds number D, right? And I'm gonna write the thermal boundary layer equation as well. So the thermal boundary layer equation, I'm gonna write this time only BL, boundary layer. I'm not writing the same thing. It would be X FDT divided by D, which is 0.05. The same equation I'm writing, except the Prandtl number I'm writing the new thing, right? So you're gonna have 0.05 Reynolds Prandtl and multiply D. Okay, so can you do have all the values now, right? Can you plug the values and come up with the value of the XFD? And that's the last thing that you want to do. I do have both values. If you're going to come up with the values, let me know. If it matches with mine, then you can go actually. So this value that you should be finding is 30.15 meter, and this value you should be finding is 21.04 meter. Now something to notice here for sure, right? See, there is a little bit difference on those two values. Actually, not a little bit, like quite a bit of difference, right? 30% value difference, right? Because remember, the Prandtl number for year is 0.7, right? Almost 30% difference over there. So that's why you have this thing. And here's another thing I'd like you to emphasize. This math you do before you go, okay? I want everybody to do this math, okay? No go error. So the other thing I would like to emphasize, okay, which is the turbulence. This is for laminar equation, right? For turbulence, there is no difference between hydrodynamic and thermal boundary layer, okay? Even though we are not doing the math, the book does have a question. I have the equation I will show it to you tomorrow. But did you guys come up with these two numbers? Isaac, did you come up with these two numbers? This is straightforward math, but you still want to do it. That way you'll have a practice, right? So you'll remember. Anytime you do write something, you'll remember it more. You know that, right? And as undergrad, I used to write everything. Everything is everything. Several times. This will help me big time. I hope this is going to help you. I don't know, for whatever reason, here people don't like to write. No matter how hard I try with my kid, push him as much as I can. He doesn't want to write. I can do anything. If he doesn't write, if he doesn't listen, then what can I do? But in back home, we used to write. If you write, you'll remember. Remember that. If you write, somewhere, somehow, it is going to strike in your brain. Okay, more. Remember it more. So try to write. Okay, write or type, whatever you do. Do something. Alright, guys. I really don't have time to do the overview. I'm already off past the class time, but you understand how important is the class, the last class as well, right? Everybody understand. So don't miss the class. Come on time, everybody. I'll try our best to finish it as smooth as possible. Okay.
I didn't have the exam in my bag, but I do know where it is at home. I will use Potsdam's campus to try and scan that in using my account. But I will have it today.
So the exam, you're gonna upload it today?
Now
I wanted to grade it now. Upload it now.
I can't because it's at home.
Is at home when you're going home?
I'm going home directly after I take the 45-degree data.
Okay.
And then I will upload it immediately.
If I'm gonna forgot, Chelsea remind me, okay? I'm gonna grade it anyway. So okay. Send me an email or something tonight. Okay. Thank you.
I'll send you an email as soon as I do.
Okay, perfect.
I don't know how I didn't put it back in here in all honesty.
I'm trying to finish up this writing part, so this is the transition where it happens. Okay. I'm gonna get you paper from that place now.